Hello everyone, this is Mr. Minnick, and right now what we're doing is taking a look at the right answers, what you should have come up with on this Algebra 2A Chapter 5 Introduction, this worksheet packet. There were 4 sections, and if you have questions about any of this, please don't hesitate to ask. In my class, we had worked in groups, and maybe some of the groups peeked over at some of the other pages. Maybe they didn't. I don't know how much time you all had, but anyway, here's what we're looking at. Page 1. Since bicycles have, well, bicycles have 2 tires usually. So since bicycles have 2 tires, so that's the first answer you should have come up with. We can say that polynomials with 2 terms are called, we use the prefix bi to indicate 2, so we use binomials. Okay. Now, if you've been in algebra class before, you've probably seen that or heard that word. So by the same reasoning, polynomials that have 3 terms are called trinomials. Okay, trinomials for polynomials with 3 terms. The standard form of a polynomial, this formula really scares a lot of people. For all whole numbers, let me highlight that. That's real important. For all whole numbers n. Now, if we look at n is an exponent, it's an exponent, it's an exponent, it's an exponent, okay? And it's an exponent, and it's an exponent. So, whole numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, not fractions, not decimals, not negative numbers, okay? So the exponents have to be whole numbers, and for all real numbers, a sub I. A sub I is any arbitrarily chosen coefficient of a particular term. Wow, that's a mouthful. Let me say that again. A sub I is any arbitrarily chosen coefficient of any arbitrarily chosen term. So if we choose the third term in this sequence right here, this a sub 2, in general it's an a sub I. We just use I for the arbitrary case, okay? So a2, a sub 2 is the second coefficient. It's the coefficient of the second term in this sequence. A sub 1 is the first term. So anytime we're referring to an a sub I, it's collectively all of those coefficients, okay? So what we're saying then is that the coefficients have to be real, and spending this much time on this now, I think we'll answer a question or two later. Okay, so notice a sub I has a subscript of I, which is an arbitrary value. Don't confuse that with the imaginary unit I. Okay, so the degree is simply the largest exponent found on a given term. Standard form polynomials, this will actually help somebody later down the road in one of the upcoming pages. But standard form means descending order by degree. In other words, if we have a quadratic term, a term with an exponent of 2, it should be written before a term with an exponent of 1, before a linear term. Okay, so biggest to smallest on the exponents. So the restrictions on n and a sub I indicate that the coefficients are the a sub I. So the coefficients, since they're the a sub i's, the coefficients, it says they have to be real. So real numbers is what we're looking for here. The coefficients must be real numbers, not reals numbers. They must be real numbers. And the exponents must be whole numbers. Okay, so if you think about what whole numbers are 0, 1, 2, 3, 4. So they could equal 0. And they're bigger than 0, so they're greater than or equal to 0. That's what you should have on that little line there. And then these other 2 lines, you might have struggled with coming up with something here. I didn't mean for it to be a struggle, but they cannot be fractions. They cannot be fractions. And the other thing I was looking for, if you came up with this, good. If you didn't, not the end of the world. This is probably the toughest one to come up with. Irrational numbers, okay? They cannot be irrational, like the square root of 2, okay? Because that certainly wouldn't be a whole number, all right? Well, the last part of this first page then says determine whether each of the following is a polynomial. So what you really need to ask yourself are these two things. Is the coefficient real? If that's the case, then it could be a polynomial. And then is the exponent whole? Okay. Now, unfortunately, we haven't really studied exponents yet, so some of these might be a mystery to you. But the first one, it's pretty clear. 3 is real, so is -2. The exponent here, even though it's not there, is 1. That's whole. Believe it or not, this term 3 right here, it's really 3 times x to the 0 power, because remember what the 0 power does? So in 0's whole, so the answer to this first one, yes, it is a polynomial. Okay, the first one, yes, it is a polynomial. The third one with just the 6, it's also a polynomial. Now, if we go to this one, the 8 plus 8i plus 3x, in this case, 8i is imaginary, so that's not, okay, because of that 8i right there. That's not real. That's imaginary. So if we look at this one on the end, 3, that's real. -4, that's real. 1, that's real. So the exponent or coefficients are real. Exponents are 23, 12, and 0. So yeah, that last one on the end, that one is a polynomial. Okay. So the one that's in question now is 2 plus 3x over x squared. 2 plus 3x over x squared. That's really 2 plus 3x times x to the -2nd. Okay. And you'll learn that when we talk about exponent rules if you didn't already know that. Another way you might have been able to tell here is if you graphed it, but then you'd have to probably read ahead onto one of the other pages. So anyway, if you didn't figure this one out, if you missed this one, not the end of the world, but it looks like the exponents are okay, but the exponent right here, that's actually a negative exponent when you simplify that. Okay, so this one is actually no. That one is actually not a polynomial. And that'll actually correlate to something that we're going to see in a minute when we talk about whether or not they're continuous. They're continuous. So, well, it segues perfectly into this. Let's see. Polynomial functions, when you graph them, are said to be continuous. In other words, there's a continual line. There's no breaks in the line. There's no holes in the line. There's no jumps in the line, and there's no asymptotes. We'll be studying asymptotes and talking about different kinds, vertical asymptotes, horizontal asymptotes, even slant asymptotes. So let's just look at that last thing that we thought might have been a polynomial, and we'll graph it, and we'll see the discontinuity. Okay. As soon as I could get out of my probability simulator here. So that thing that was in question, we were looking at this function 2 plus 3x. So let me group that numerator. Group the numerator, 2 plus 3x. That numerator divided by the group of x squared. Okay. So when we graph this, we're looking for a continual line. And let me do a zoom 6, a standard viewing window. And that's not a continual line. It kind of does some weird stuff. If I calculate a value when x is 0, the y value doesn't exist. So that means that particular function is discontinuous and it's not a polynomial. Okay. So as such, there should be arrows on the extreme ends of the graphs indicating, there's a typo, sorry about that, indicating the graphs continue on forever in either direction. This tells us that the blank of a polynomial function is the set of all x's. Well, all the x's that are possible are from -infinity to positive infinity. Hopefully you remember the definition of what that is, all the possible x values of a function. That's its domain. That's its domain. Okay, so that's what we're looking for on that first blank. So here we're talking about end behavior. What happens on the left end of the graph? What happens on the right end of the graph? Okay, 2 factors will tell you this: the degree and the leading coefficient. The degree remembers the exponent, the term with the biggest exponent, and the leading coefficient. Now, this is assuming that this makes a big assumption. It makes the assumption that you put the function in standard form. In other words, you're only looking at the first term when the function is written in standard form. So a couple of these you're going to have to think about that. So we're going to graph these functions. We're going to see if the function's going up or down on the left and on the right, and then we're going to make a conjecture. Okay, so the first couple were done for you. Let me bring my calculator back up here. And let me put on my axes. I'll put those back on. Okay, so my axes are back on. Let me turn the smart ink off. That's going to interfere. So here we go. We graph y equals x. We've seen that. On the left it goes down, and on the right it's going up. Okay, and then we've graphed x squared. On the left it's going up, and on the right it's going up. Okay, so the next one that you're asked to graph here is negative 3x to the 6th. So this one on the ends goes down on the left end and down on the right end. Okay, so this is down and down. This next one, 4 minus, now that one's not in standard form. If we put that in standard form, the leading term would be negative 5x to the 4th. Okay, so watch this, 4 minus 5x to the 4th. Our leading term is really negative 5x to the 4th, and the leading coefficient is really negative. Watch the end behavior here. Down on the left, down on the right. Okay, so this next one is also down and down on the ends. Okay. The next function that we're graphing here, 16 plus 4x plus 8x to the 5th. 16 plus 4x plus 8x to the 5th. So one thing I want you to realize here, the first term is really the only term that matters. This goes down on the left, and we can't really see what's going up on the right, but we're assuming it's going up, so it's going to be down and up. This one's down and up. Okay. What would happen if I got rid of this 16 and made it 4x plus 8x to the 5th? Still going down on the left and up on the right. What happens if I get rid of this 4x and just make it 8x to the 5th? Well, it's still going down on the left and up on the right. So the first term really is the only term that tells us about the end behavior, and it does. So really we can almost kind of disregard the other terms. Okay, so hopefully you made that connection. X to the 7th, x to the 7th. On the left goes down, and on the right goes up. So that one's down and up. Negative 3x to the 5th, negative 3x to the 5th. Remember what a negative out front does. It inverts something. So hopefully that kind of gives you an idea of what's going to happen here. That's not going to work what I just have. I said negative 3x to the 5th. Got to make sure I get that x in there. So when I graph this on the left edge, this is going up, and on the right edge, this is going down. So up and then down. And this last one, 4 plus 5x to the 4th, hopefully this one makes it real clear that 4 plus 5x to the 4th. Really, the first term's the only one that makes a difference. And then this one's up and up. This one's up and up. So whenever the leading coefficient is positive, such as in this one, oh, I meant to change colors there. When the leading coefficient is positive, so F1, F2, F3, F4, and F5. Whenever the leading coefficient is positive and the degree is odd, so that's going to be this one, and this one again, and this one again, the end behavior is down and up. Okay. Whenever the leading coefficient is positive and the degree is even, well, that's the other ones. That's there's only two more that's left. Positive and even, then we are looking at up and up there, okay? Up and up. When the leading coefficient's negative, do we have one? Yeah, leading coefficient is negative and the degree is odd. We're looking at um, up and down there, up and down there. And then when the leading coefficient is negative and the degree is even, we're looking at down and down there. Okay. So one thing that I personally do to keep these organized is I just think of y equals x squared versus y equals x. Okay. If we had y equals 7x to the 10th, it's going to either follow the same pattern as this or this. Well, it's going to follow the same idea as this. Okay. Well, what about this? Negative x squared. Okay, so it's either going to follow one of these four patterns then. Y equals negative x. Okay, so let's think about y equals negative x to the 5th. Okay, well, that's going to be like this one. So if you know the end behavior of those, which are pretty basic functions, you should be able to figure these out relatively quickly without a graphing calculator. What about y equals 2x minus 8x to the 7th? Okay, well, the leading term there is minus 8x to the 7th. So that whole thing, collectively, that whole thing is going to be similar to a line that opens, well, that has a negative slope. So the end behavior there should be up and down. And if you want to just test that theory, quickly, let's graph this. 2x minus 8x to the 7th. Okay. So this whole idea with end behavior, it really all just comes back to the first term or the leading term. And here's our end behavior, up on the left, down on the right. Okay, just like that line would do. Okay, so hopefully that kind of makes a little bit of sense and you're doing okay with these. I think we're going to end up making this video a two-part series. So this is the first of two parts. It's been fun. If you have questions, please ask, and I'll see you in the next episode.